So the next speaker is Riley Roberts, and the title of the talk is Stamina 2.0, Improving Scalability of Infinite-State Stochastic Model Chain. You can start.
Okay, can you hear me and see my slides?
Yes, we can.
All right, thank you. Yeah, like she said, my name is Riley Roberts, and I'm presenting our paper Stamina 2.0, Improving Scalability of Infinite-State Stochastic Model Checking. This is a joint work between myself and the other individuals listed here. Stamina is a stochastic model checking, or SMC, tool. Stochastic model checking is the formal verification of systems that have probabilistic characteristics. One requirement for performing SMC is that all possible states must be explicitly generated and stored in memory. Many real-world systems can be modeled as continuous-time Markov chains, or Ctmcs, and these often have large or even infinite state spaces for real-world use cases. For these particular models, SMC can be infeasible due to the memory constraints, particularly when dealing with the infinite state systems. There are a few existing tools that try and deal with this problem. Lately, satisfiability modulo theories, or SMT-based approaches, have had a lot of success on large DTMCs, but they have not yet been extended to the infinite state or Ctmc domains. STAR and Sequoia are both tools that are able to do model checking on infinite state biochemical reaction networks, but they focus on state reachability probabilities rather than checking arbitrary properties. INFAMY was one of the first tools that was able to quantitatively verify infinite state Ctmc models. And it does so by generating the state space up to some finite depth and then truncating from there. And then Stamina 1.0 is the previous version of the tool I'm presenting here, and I will go over it in the next few slides. So Stamina 1.0 was created to model check continuous stochastic logic, or CSL, properties on Ctmc infinite or large state space models. It does so by iteratively exploring a portion of the state space, then model checking using Prism, and then exploring more if necessary. It guides this exploration towards the more probable portion of the state space, where probable is determined by an estimated value that we compute as part of our state space construction. It also has property-guided early path termination, indicating that when a state is reached that is known to not satisfy or satisfy the property, that state's outgoing transitions are not explored, because all paths that pass through that state are now known to either satisfy or not satisfy the property. And then it's able to calculate a probability window within which the true probability of a property is known to lie. The more states that are generated, the tighter this probability window becomes. But the idea is to use that window to get a relatively accurate answer to the property in question without needing to generate nearly so many states. In order to understand how Stamina 1.0 works, there's a few things of terminology that we first need to clarify. We term kappa the reachability threshold, where below this threshold, all states with a estimated reachability lower than that will not be explored. We define S as the set of all explored states, and T as the set of terminal states, where a terminal state is defined as a state whose estimated reachability is below kappa. Then we route all outgoing transitions from states in T to an artificially created absorbing state S hat that we will use to keep track of the probability of reaching a state that we have not explored. Because we're not exploring a large portion of the state space, in order to determine the true probability bound, we need to know the probability of reaching those states that we have not explored. The general architecture of Stamina 1.0 looks like this, where Stamina is given a kappa, and then it produces S and T, which it passes to Prism, and we have implemented using some Prism APIs the proper way to generate the probability min and probability max for a particular property given S and T. We then compare the width of that probability window to a user-defined probability window, which we deem omega. If it is tight enough for the user specifications, we are done and we return the window. If not, we reduce kappa and expand further to tighten the window. And that probability window is created in the following way. For any non-nested CSL property, where we're looking for the probability of psi being satisfied, we have that the minimum probability is phi and not reaching the absorbing state. That's the probability of reaching or having the property be satisfied without getting to states where we have not explored. And then the maximum probability is the probability of phi or the absorbing state, which is the probability of the property being satisfied or us reaching some state that we have not yet explored, where we're assuming in the worst case that the property would be satisfied in all non-explored states. And so because we haven't explored those states and we don't know what's going to happen there, we have to assume that they would all satisfy in the worst case. For Stamina 1.0, we derive the estimated reachability in the following way. The reachability probability from S to S prime is the exit rate from S to S prime divided by the sum of all exit rates out of S. And we denote this P of S, S prime. We call the estimated reachability of state S pi hat of S. And then we calculate pi hat of S prime as the sum over all predecessor states of S prime, or all states that have a transition to S prime, with the sum of the multiplied reachability of that predecessor by the reachability probability of the transition. For Stamina 2.0, we provide several improvements to the original model. First, we do combined Ctmc analysis so that we do not have to run a separate Ctmc analysis to derive probability min and probability max. We also put forward a new method of reachability calculation that is more efficient and tends to produce more accurate estimations. And we also restructure the algorithm in order to alleviate some issues that will be discussed and allow the tool to find the more probable portion of the state space. For the combined Ctmc analysis, Stamina 1.0 required invoking Prism 2 separate times, which was costly, particularly for larger models. Instead, we've changed that to a single transient analysis, which we perform to give P sub T of S, which is the probability of being in state S at time T. The minimum probability is simply the sum of all PT of S where S satisfies the property. Because we have the property guided early termination, if state S satisfies the property, that state becomes an absorbing state and we will remain in that state from that point forward. So if we reach it in less than time T being the time that we're trying to check the property for, we will remain in that state at time T. And then the maximum probability is simply the minimum probability plus the probability of reaching or being in the absorbing state at time T. In order to understand the other two improvements, we first have to define a problem that was occurring in Stamina 1.0. We call it the trapped reachability problem. This figure here shows a state space that is being incrementally constructed. So all three show the same state space at various points during exploration. Portion A just shows a state space with 5 states where we have determined the estimated reachability of state 3 to be 0.1 and state 4 to be 0.9. State B shows that the next thing we do is explore state 5, and we see that it had reachability 1 from state 3, giving it an estimated reachability of 0.1. Then as we go to C, we then explore another transition from state 4 to state 3. This raises state 3's reachability to 1, but we cannot re-explore state 3 in order to pass that reachability on without running into issues of infinite loops during our exploration and reachability estimation computation. So at this point, we say that that reachability has become trapped in state 3 and we're unable to pass it on to state 5, even though it's obvious that state 5 should now have a 1.0 reachability. Stamina 1 did have an attempted solution to this problem. After state exploration, it would simply forcibly re-explore all the terminal states and then repeat that re-exploration until the change in state space size was sufficiently small, where sufficiently small was defined by a heuristic. However, this was computationally complex as you had to loop through all the states to determine which ones were terminal and re-explore them one step at a time as you wait for the state space size to change a small enough amount. It also doesn't help when the reachability is trapped in a non-terminal state. For Stamina 2.0, in order to fix this problem, we first had to change the way reachability was calculated. In order to re-explore states, we have to make sure not to pass on reachability twice. If we've already given reachability from a particular state to its successor states, and then we're going to re-explore that state, we need to make sure to only pass on the new reachability that has come to that state since the last time it was explored. In order to do that, rather than calculating reachability as the sum over the predecessors, we instead calculate the reachability on the forward path of exploration, where each time we explore a new state, we pass it the proper reachability from its predecessor state as we're going. And then after we've fully explored a particular state, we reset its reachability to 0, indicating that all of its reachability has now been passed on. And if we encounter that state later in our exploration and it has some reachability, we know that that must have come either from a looping structure or from a newly explored transition into that state, and that we can safely pass it on again. Doing this is actually more computationally cheap than the previous method, because instead of having to loop over a list of predecessors each time a new transition to a state is discovered, we simply do the computation as we're exploring the transitions out of the current state, which we had to do anyway. This set the stage for us to perform the major algorithm changes, which are that after we finish with a particular kappa, we now re-explore the entire state space, beginning with the initial state again, with the idea that we're allowing trapped reachabilities to be pushed throughout the state space as we forcibly re-explore all states. You can see that this would obviously be computationally intensive to start over again. And previously, we had to model check between each change of kappa. So we had to change a few things to make this work. First, instead of a user-chosen kappa, we start kappa at 1 and reduce it gradually over time. And we also don't model check after each reduction. Instead, we have a probability window estimation that we come up with to determine when we should complete and pass on to the PRISM model checker. That estimation is simply the threshold multiplied by the number of terminal states. So that's just a simple calculation we can make to produce this estimation without excess computation. Because it is only an estimation, it often does not match up with what the true probability window will be exactly. So we also divide the desired probability window size by a misprediction factor prior to comparing to the estimation to determine when to complete model or pass it to the Prism model checker. We then model check with Prism, and if we did not achieve the desired probability window, we grow the misprediction factor relative to the amount of error between the actual probability window and our estimation, so that on future iterations, we come closer to the true probability window. Making these algorithmic changes fix the trapped reachability issue, which allows Stamina to have much more accurate probability estimations and then pick better paths to explore. When we pick these better paths, we find the proper portion of the state space faster, where the proper portion indicates the portion with the most probability mass relative to the property being checked. And the additional speed and accuracy at finding this proper portion of the state space far outweighs the extra computational burden in all of our testing. In addition, in the previous version of Stamina, the user had to choose the initial value of kappa, pretty much using no particular method. It was very difficult to determine a good kappa for a particular model, and each model needed a different kappa, where now a relatively optimal kappa is found dynamically, alleviating the user of picking that themselves. For the results that we're going to show here, we're showing the improvement measured as the percentage decrease for both runtime and state space size. So 50% would indicate runtime or size were halved, and 100% is the maximum possible, as that would indicate a decrease to 0. And the formula used for percentage decrease is shown there. So the first model that we tested this on is a genetic circuit that shows a glitching behavior. We call it the hazard circuit. Namely, during an input change, when the output is supposed to remain high, it can occasionally glitch to low. And originally, Stamina 1.0 struggled to produce results with this model, which was what spurred the investigation into Stamina 2.0. The labels on the bottom of the chart here indicate the transition of the input. For example, the far left has 010 to 111. That's showing the input is transitioning from 0, 1, and 0 to 1, 1, and 1. And there is some probability of a glitching behavior during that transition. Stamina 1.0 was not able to generate an adequately tight bound for some of these models, even after we tuned the kappa manually. We started with 1e to the -3, and none of the models were able to complete. We changed it to 1e to the -6 or 10 to the -6, and eventually found that 10 to the -35 was the required kappa to get Stamina 1.0 to complete on these models. And even then, the models that are underlined in red, Stamina 1.0 was still not able to achieve the desired probability window tightness of 0.001. So that just shows that even after manually tuning kappa, Stamina 1.0 could still fail to produce results just because it's hard to find an optimal kappa, where Stamina 2.0 just was used with default parameters for all of these testing. We can see that for many of the models here, Stamina 2.0 had approximately 90% reduction in both runtime and state space size. And for the models that it did not have as high of a reduction, it was because Stamina 1.0 actually did not complete. And so the probability window was not actually tight enough, but Stamina 1.0 was forced to terminate due to memory or iteration count limitations. This table here shows the actual computed windows for those models that Stamina 1.0 was not able to complete an adequately tight bound. For example, the very top transition, 010 to 111, you can see that Stamina 2.0 was able to produce a very tight bound, looks like 0.0002 as the probability width, where Stamina 1.0 is fairly large, almost meaningless wide bound. And keep in mind that for these different bounds, Stamina 2.0 was still able to produce that result with more than 50% less state count and still close to 90% less runtime. We also tested Stamina 2.0 against the original suite of benchmarks that Stamina 1.0 was tested on. Stamina 1.0 at the time it was tested on these was compared to INFAMY, the other model checker. So we did that comparison here as well. You can see that for these models, Stamina 2.0 still achieved relatively high improvements versus both INFAMY and Stamina 1.0, but not quite as good as the 90% reductions on the hazard model. That's because these models are much simpler and not as large as the hazard models were. So there's just not quite as much room for improvement. There are a few special things to note on this particular graph. First off, the polling example here, you can see that Stamina 2.0 had near 99% reductions compared to Stamina 1.0 and INFAMY. This is because the polling example actually satisfies its property in the initial state. INFAMY is not able to recognize that as it just explores a finite depth. Stamina 1.0 does have the property-guided early termination, but because of the method they were using to try and fix the trapped reachability problem, it was still required to generate many more states than just the single state required, where Stamina 2.0 is able to recognize that only one state is needed and quit there. Also, something to note, you can see that the Jackson model with parameters 4 and 5 is the only model where Stamina 2.0 did not have a state count improvement relative to Stamina 1.0. It actually required slightly more states. An explanation for this is that Stamina 1.0 does use the manual kappa selection. And if that manual kappa does happen to be optimal for a particular model, Stamina 1.0 still will generate a optimal number of states in the state space size. But it cannot be counted upon for the user to select that kappa, as there's no real methodology for choosing it. And Stamina 2.0 was still able to achieve greater than 40% reduction in runtime for that particular model. In conclusion, Stamina 2.0 was able to achieve significant reductions in both runtime and memory usage, which allowed it to obtain results for models that it previously could not. In addition to opening up the availability to model check infinite state models that are relatively complex and cannot previously be implemented. For some future work, we're hoping to integrate this tool with Storm as well as with Prism, which it's currently integrated with. And we're also hoping to incorporate time information into our reachability estimation, as currently we do not use that. Thank you. Are there any questions?
Okay, let me get started. So you mentioned you were looking at the non-nested version of CSL.
Yeah.
How would all of this work if we were to look at the nested versions?
Honestly, I have not been working with any nested CSL properties. I'm not particularly sure how it would work. I know that a previous student did look into that and determined that the current method wouldn't work, but I haven't been involved in any research with what needs to be changed to get it to work for nested CSL properties. But I can say that it's simply the early path or the property guided early termination that wouldn't work with nested CSL properties. The general reachability estimation and state space truncation should still work for any type of property. We just wouldn't be able to implement the early termination step.
Right. And most of the properties that you looked at, were they reachability or were they more temporal? Experiments.
They're mostly the of the form true until some thing. So we're mostly looking at the probability of a particular value going over some threshold within a period of time.
Other questions? We are slightly ahead of schedule. Let's thank the speaker and then we'll set up.